Good morning, class. We are looking at polar equations and graphs, section 8.4, polar graphs. So the objectives are to identify and graph polar equations by converting to rectangular equations, test polar equations for symmetry, graph polar equations by plotting points. Again, formulas that we have seen, basic trigonometric identities, everything from odd and even function to fundamental identities, to sum and difference formulas, reminding you of the sine and cosine law and the equation of a circle that is really handy. Double angle formulas are here, and as a result of this one, cosine has three different ways, and it gives rise to sine squared alpha. And then if you cut this into 2, alpha over 2, this becomes alpha. And this green gives us cosine squared, and of course tangent is the ratio of sine over cosine. Half angle formulas, so we can take a root of these half angles and come up with the answers. We have also added product to sum and sum to product formulas in case somebody is interested. We discussed the polar coordinates. Remember, we have a grid, a rectangular grid has a point has coordinates x comma y. Polar axis is the positive side of the x-axis, and here's the pole. And when that happens, a point has coordinates x comma y or r comma theta. Now, r comma theta is not unique. So in the case of a rectangular, a distance from the y and x-axis, polar, a distance from a reference point called the pole, and the angle from a reference direction called the polar axis. Rectangular has coordinates x comma y. Polar has coordinates r comma theta. X squared plus y squared is r squared. This is how we find r. And tan of theta is the ratio of y to x, and we have to adjust for the quadrant to figure out whether theta is positive, negative, and so forth. And of course, x is r cosine theta, y is r sine theta. And as I mentioned, r comma theta is not unique. Therefore, you can write infinitely many format. We can add 2k pi, or if you want to change the r to minus, we have to add pi or odd multiples of r. K is an integer, everybody. And now we want to go to the new stuff, polar equations and graphs, rectangular and polar grids, as of course everybody is familiar with rectangular grid versus polar grid. So we draw various circles. That would be one easy way to do that. And of course, we draw lines that represent various angles. For example, this is theta equal to 0. This is theta equals pi over 4. This is theta equals pi over 2, 3 pi over 4 pi, and so forth. So everybody is familiar with the angles. So for example, if you are on the second circle, r is 2, and on this line, theta equals pi over 4. A polar equation of a curve is the one expressed in polar coordinates and written with r as a function of theta. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. These equations may demonstrate different forms of symmetry around the axes. So we have r equals 3. We want to identify the graph of the equation, convert it to a rectangular equation, and again, reminding everybody of x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, tan theta equals y over x, all of the, and so you may remember when we have r, basically it really represents a circle. So if you square that, you get r squared equals 3 squared and r squared is x squared plus y squared. 3 squared is 9. So we are looking at a circle centered at 0, 0 with the radius r. Now, so when r equals to 3, we have a circle with the center at the pole with the radius of 3. This is easier than this one if we were to represent a circle which is centered at the origin or pole. This would be an easier representation. So that's easy graph. Basically, a circle with the radius 3 centered at the pole or 0, 0. Theta is pi over 4. We want to convert it to a rectangular equation. So theta is pi over 4. The trick is to take a tangent of both sides. So tan of theta is tan of pi over 4. Now, what is tan of theta? Y over x. What is tan of pi over 4? It's just a number. Even if it's not a common arc, you can use a calculator. This is some number. In this case, of course, is 1. And of course, the cross product will give you y equals x. As you know, y equals x is a line through the origin, okay, with the slope m equals 1. So theta equals pi over 4 or y equals x. You can think of the rectangular grid, okay, y equals x. So theta equals a number. So when we are given the angle, it becomes a line through the origin. For example, if theta equals pi over 6, then this would be the line with the angle pi over 6. What about r sine theta equals 2? R sine theta equals 2. So r sine theta equals 2. We look for r sine theta if we have it here. And we know r sine theta is y. So basically replace the r sine theta with y. Right here. And you know that's a horizontal line. So r sine theta equals any number. Gives you a horizontal line. If it's 7, y equals 7. If it's 10, y equals 10. If it's negative 1, y equals negative. You're learning about different types of polar equations. Over here, we have r cosine theta equals negative 3. R cosine theta equals negative 3. Well, what happens here? Very simply put, we look for r cosine theta. We recognize r cosine theta as x, if you will. That's the methodology, recognition. And therefore, x equals minus 3 is the answer. And as you know, that is a vertical line, everybody. That is a vertical line. So very straightforward, everybody. let's say it was r cosine theta equals 5 would be a vertical line on the right side. All right, r equals 4 sine theta. We've done this before in the previous section. When that happens, the technique is to multiply both sides by r. Left side becomes r squared, right side becomes 4r sine theta. Left side r squared, we know it to be x squared plus y squared. Right side r sine theta can be replaced by y, so we have 4y, and you may recognize it from algebra that is a circle. You have to come up with details, meaning we are going to move the 4y to the left, becomes negative 4y. We are going to complete this square. This is b. B divided by 2 is negative 2. We are going to square that. Gives us positive 4. We are going to add positive 4 to both sides. This is x squared. This is y. And it's always plus b over 2. B over 2 happened to be minus 2. So y minus 2 quantity squared on the right side is 4. And again, we have r equals 4 sine theta, or x squared plus y minus 2 quantity squared equals 4. These two are the same. And we know this is a circle. I'm reminding you of the general format, x minus h quantity squared plus y minus k quantity squared equals r squared, has the center at h and k, whereas this one had the center at 0, 0. So this has a center at 0, 2, radius is square root of 4 or 2. And that we come up with the center and the circle. All right. R equals negative 2 cosine theta. Same technique. Multiply both sides by r. So this gives you r squared. This gives you negative 2r cosine theta. The reason we do that, because we notice r squared is known to be x squared plus y squared. And we know if we had an r here, r cosine theta is x. So now we're going to replace the r squared with x squared plus y squared minus 2 r cosine theta is replaced by x. So minus 2x. So this part is x. Again, the same as before, we bring it to the same side. So we are going to move the negative 2x and put it next to x squared. We are going to complete this square. And as you know, this is b. So b divided by 2 is 1. And if you square that, again, you get 1. Let's add 1 to both sides. This is x plus 1 quantity squared. The rest you write it. So in the case of r equals minus 2 cosine theta, or x plus 1 quantity squared plus y squared equals 1, we end up with a circle. Both are the same. Both represent a circle centered at negative 1, 0, The radius is square root of 1, which happened to be 1. So again, the center is at negative 1, 0, because remember we have x. Let me write this, so I want to make sure everything. So this is x minus h quantity squared plus y minus k quantity squared equals r squared. That's why for this one, you get negative 1 comma 0 as the center. So I can't emphasize this enough, everybody. All right, we are going to move on. And this is the graph, everybody. First recognition of this is important. You come up with the center. Radius is 1. Graph it. And you're done. So, in short, we have the following theorem. When R is a number, any number, R equals A represents a number. We are dealing with a circle centered at the pole with the radius A. When theta is a number, theta equals alpha, beta, gamma, then the line is y equals tan alpha times x. Because the technique is to take the tangent of both sides and replace the tangent with y over x. And so it ends up being y equals tan alpha times x. HL, horizontal line, or sine theta equals A, it ends up being a horizontal line. Y equals A. Y equals A. Vertical line, short VL, or cosine theta is a number, or cosine theta is a number, then x equals A. X equals A. We are assuming A is a positive value. R equals 2A cosine theta. R equals minus 2A cosine theta. R equals 2A sine theta. R equals minus 2A sine theta. All of them represent some sort of a circle. In this case, R is A, and the center is located at A0. Actually, all of them, the radius is equal to A. The center, A comma 0, the center minus A comma 0, the center 0A, and the center is 0 minus A. So if it involves cosine, the circle is along the x-axis. If it involves sine, it's along the y-axis. That's really the bottom line, everybody. All right, we are going to move on. So this is the synopsis of what we just did, everybody. Those examples we did, they involved a basic circle, a line through the origin, horizontal line, vertical line, and a bunch of circles where the center was located either along the x in the case of cosine or along the y in the case of sine. Symmetry in polar coordinates, symmetry with respect to, I'm going to use WRT, with respect to the polar axis. Polar axis works like an x-axis. If in the polar equation r comma theta can be replaced by r comma negative theta, because theta is positive here, negative on this side, right? Resulting in an equivalent equation, the graph is symmetric with respect to the polar axis. So if we could change the theta to negative theta, we have a symmetry looking like that. R comma theta, R comma negative theta. So it's symmetric with respect to the polar axis, or you can think of it as x-axis. Symmetric with respect to the line theta equals pi over 2, which is really in essence like the y-axis. Theta equals pi over 2 is the y-axis. If in the polar equation r comma theta can be replaced by r comma pi minus theta, the graph is symmetric with respect to the line theta equals pi over 2, or the y-axis. So this is, again, the y-axis, or theta equals pi over 2. So if we have r comma theta versus r comma pi minus theta, pi minus theta. Symmetry with respect to the pole or the origin. If in the polar equation r comma theta can be replaced by negative r comma theta, or r comma theta plus pi, the graph is symmetric with respect to the pole. So r comma theta, all we have to do, negate the r. So it becomes symmetric with respect to the origin or pole, if you will. Or if we could say r comma theta plus pi, you have to check both of them. And when both of these do exist, results in this case also. Now we want to graph r equals 1 minus sine theta, everybody. We want to graph this, and basically you can just plug in, and I'll show you that concept as well. But let's discuss the symmetry. And I remind you of the previous page. So we are going to check the symmetry, starting with the first one, polar axis. We are going to look at the equation, and we are going to change the theta to minus theta. If we get the same equation, it is symmetric. If we don't, we don't. So if I replace the theta with minus theta, as you know, this is minus sine theta, because sine, all trigonometric functions are odd functions with the exception of cosine, and therefore secant. So negative times negative makes it positive. And this is not the same as the original function. The test fails. Let's replace the theta with pi minus theta, see what happens. Replace the theta with pi minus theta. We are looking at the second case. All right, sine of pi minus theta. I'm reminding you that is sine pi cosine theta minus cosine pi sine theta. In other words, okay, sine of alpha minus b. As you know, sine of pi is 0. And cosine of pi is negative 1. So this negative times negative makes it positive. 1 minus positive sine theta makes it 1 minus sine theta, and therefore it makes it symmetric with respect to theta equals power 2. Let's replace the r with negative r. So if I replace the r with negative r, in order to get back to this, I have to multiply both sides by negative, so that if I'm replacing r with negative r, multiplying by negative 1 results in r here, minus 1 plus sine theta here. And are they identical? No, so that doesn't work. So the second one is to replace the theta with theta plus pi. And as you remember, sine of alpha plus beta, I have a plus sign here. So I'm going to expand this in the same manner, just like this one with the plus in between. Okay. And of course, sine theta cosine pi plus cosine theta sine pi. So cosine pi, we know it to be -1. Sine of a pi, we know it to be 0. Now this we don't have to worry about it. This becomes negative, and with this negative becomes positive sine theta, and therefore it's not symmetric with respect to pole. Pretty straightforward.
I have a question.
Go ahead.
I see that the last one we do in two-way, but why are the equations different?
What do you mean the equations are different?
To the left, we have like -1 plus sine theta, and to the right, we have like 1 plus sine theta.
We are just trying to check the symmetry. If it works out, if you look at the first one, this is the answer, whereas this is what we are looking for. We are checking for symmetry. We plug in negative theta. If we get the same equation, they are symmetric. In this case, we got 1 plus sine theta. In this case, we got -1 plus sine theta. In this case, we got 1 plus sine theta. None of them is the same as the original one. Whereas here, when we did with respect to theta equals power 2, and we replaced the theta with pi minus theta, notice here, when we did that, it ended up with a situation which is identical to what we started, and that means the graph is symmetric with respect to theta equals power 2. So again, you're checking for symmetry. Okay?
Yes.
So we are going to graph this, and it results in what we call a cardioid, and we need to plot pairs. Now, from 0 to 2 pi, you can take as many points as you want, but it's a good practice to take easy ones. For example, 0. Because it's a common arc, you know this is 0, so 1 minus 0 is 1. Okay? Pi over 6. Pi over 6, you know sine of theta is what? 1/2. So 1 minus that makes it 1/2. Pi over 4, square root of 2 over 2. So 1 minus square root of 2 over 2. Pi over 3, 1 minus sine of pi over 3, which makes it 1 minus square root of 3 over 2. Pi over 2, 1 minus sine of pi over 2, which means 1 minus 1 equals 0. And the rest of them follow. So r equals 1 minus sine theta. And again, the reason I've chosen those because of the fact those are all common arcs. Now we are going to write r comma theta. For example, this one is 1, 0. This one is 1/2 pi over 6. This one is 1 minus square root of 2 over 2 pi over 4, and so forth. So we have chosen the angles. We have come up with the value of r. We have calculated those. By the way, 2 pi goes back to 0, right? The value. And we write the pairs. All we have to do, come up with those pairs. Now, this may not be to scale, but assuming that each circle represents 1. So, for example, this is 1 tick mark, 2, and 3 tick marks. This is not to scale, but to give you an idea. If I want the first one, 1, 0, okay, so I go right here, okay, because this is 0 degrees. First, you really have to come up with the angle, 0 degrees, and you go 1 tick mark. So that's your point. 1/2 pi over 6. So assuming this is about pi over 6 and this is 1, so about 1/2 is roughly here. Okay. Again, rough, maybe not exact. And again, I want to jump from this 2 to this one because this is an easy choice. Pi over 2, 0. Okay. First, you go with the angle. I have done the 1/2 5 pi over 6 first. That's fine. So about 5 pi over 6 is here, and you go 1. Again, this is not to scale. This one, class, is 0 pi over 2. This one is 0 pi over 2. By the way, if you have 0 with any angle, change it to any angle, it represents the pole. Okay, with any angle, you end up here. There is a reason I'm using different colors here. Again, this is not to scale. I couldn't put it in a right spot. 1 pi. So first you go look at pi, this direction, and you go 1. Okay. This one is 1/2. So it maybe should be closer to this, but I tell you why I did them in different colors in a moment. 2, 3 pi over 2. Class, this is pi over 2, this is 3 pi over 2. So 1 and 2 tick marks. 3/2, 11 pi over 6. So this is 11 pi over 6. Or minus pi over 6. And 3/2, about 3/2 is about 1.5. Now, why did I do that in different colors? Because if we go back to this, remember the graph is symmetric with respect to theta equals pi over 2. So if you were to graph this part only, I'm going to graph it and I'm going to erase it in a moment. So if we were to do, let's see what color, let me just, okay. So it will look something like this. Just look at this half, never mind the rest. So this one, because it's symmetric with respect to theta equals pi over 2, on the left side should look the same. So let me use a different color. So on the left side, you can use the symmetry and graph it. And again, this is not to scale. I'm going to erase it and show you a better graph, but that's the concept, everybody. So let me erase that. And that's the cardioid when we have 1 minus sine theta or even 1 plus sine theta and so on. All right, let's look at 1 plus sine theta. I want to look at a different approach just so you're exposed to it. we can graph this in a Cartesian coordinate system. If you recall, this sine theta looks like that, and you move it up, right, by 1. So let me again graph, then I erase it. So this is sine theta, right? And then 1 moves it up by 1. So it looks like that. Okay, so it looks like that. So let me erase it. So this has been shifted up, okay? So let me erase this. And so we're gonna read the values of R corresponding to increasing values of theta. This is the second approach. So stages in sketching the cardioid. This is also called the cardioid, 1 plus sine theta. So as you recall, we had 4 arcs, 1, 2, 3, 4. So as theta increases, okay, look at this one. So we go from 0 to power 2, and the value of y goes from here to here, from 1 to 2. So as theta increases from 0 to pi over 2, R increases from 1 to 2. So theta is 0, R is 1. Theta is 0, R is 1. Theta is pi over 2, 1 and 1, 2. So it looks like that. Theta equals 0, R is 1. So this point, R comma theta, 1 comma 0. This one, 2 comma pi over 2. This is the first stage. The second stage is the second arc. As theta increases from pi over 2 to pi, R decreases from 2 to 1. When theta is pi over 2, we had 2 anyways. When it's pi, sine of pi is 0, we get 1. So it moves such that this one has coordinates 2 pi over 2. This one has 1 comma pi. 1 comma pi. Maybe I write those. As theta increases from pi to 3 pi over 2. So from pi to 3 pi over 2, it goes from the value of 1 to the value of 0. So when theta is pi, R was 1. What happens when we put 3 pi over 2? This is negative 1 with 1 adds up to 0. So looks at this point and this point as coordinates 0, 3 pi over 2. As I've mentioned it before, by the way, the pole has coordinates 0 with any angle. Normally we say 0, 0, but it can have any angle. And finally, as theta increases from 3 pi over 2 to 2 pi, it goes from 0, the y coordinate is 0, here, and the y coordinate is 1 here. It goes from 0 to 1, which means when theta is 3 pi over 2, we know R is 0. If it's 2 pi, when you plug it in here, 2 pi becomes 0 and 1 is 1. And it goes like that. This is the second method. Again, I'm going to quickly recap. You could graph this in a rectangular coordinate system, cut it into 4 arcs. Okay, 1, 2, 3, 4. 1, 2, 3, 4. It's a good practice. You give it a shot and see which one works the best for you. We want to graph r equals 1 minus cosine theta. We are basically interested in plotting pairs. And now this gives rise to the following theorem. R is a times 1 plus minus cosine theta, or R is a times 1 plus minus sine theta when A is positive, passes through the pole, and it's a cardioid. So again, let's look at easy numbers. For example, theta is 0. Cosine of 0 is 1. 1 minus 1 is 0. If it's pi over 6, cosine square root of 3 over 2. 1 minus square root of 3 over 2. If it's pi over 4, 1 minus square root of 2 over 2. Okay. If it's pi over 2, this is 0. So 1 minus 0 or 1. If it's 2 pi over 3 is 1 half, negative 1 half. So 1 minus negative 1 half makes it 3 halves. If it's pi, it's negative 1. Minus negative 1, positive 1, so makes it 2. So those are the values from common arc. And these are the pairs. Again, 0, 0, 1 minus square root of 3 over 2 pi over 6, and so on. So let's plot a few of them, easy ones. For example, 0, 0. So those square root of 3 is about 1.71. You have to divide by 2, subtract it from 1. Square root of 2 is about 1.41. So divide by 2, subtract it from 1. We want something easy. For example, 1 half and pi over 3. So you go by pi over 3 and 1 half. We are assuming that each circle represents 1 half, okay, and 2 circles represents 1. The next one is 1 pi over 2. Pi over 2, in essence, along the x-axis. And remember, 1 is, in this case, we are choosing each circle to represent half. So this is half, this is 2, okay? And 2 of them is 1. 2 and pi, we can go with 3 halves and 2 pi over 3, okay? 3 halves is 1.5. Okay, somewhere there. Again, this is almost on that. This is not to scale. It should be right here. And 2 pi. So pi is on this side. 1, 2, 3, 4 means 2. So somewhere here. And so the graph looks like that, everybody. Looks like that. Let me draw it on our eraser. This is obviously not to scale, doesn't look too good, but something like that, or looking like that. Now, if we go through the symmetry or plotting the rest of the points up to 2 pi, we can figure out the rest. So, for example, r equals 1 minus cosine of negative theta is, and I'm going to do just that one. If I replace the theta with negative theta, I'm checking the symmetry. Checking the symmetry, because I notice quickly that it's the same thing, right? And so it's symmetric with respect to the polar axis, with the x-axis in essence, right? So this is the other half. So repeat this right here. symmetric with respect to this line, y equals x or the polar axis. R theta can be replaced by r comma minus theta, resulting in an equivalent equation. The graph is symmetric with respect to the polar axis. And if I were to pick more points, for example, 4 pi over 3, cosine of 4 pi over 3 is the same as cosine of pi over 3, but negative, so makes it negative 1/2. Minus negative 1/2 makes it plus 1/2, so it makes it 3/2 here. 3 pi over 2, we know cosine is 0, so it's just 1. 5 pi over 3, in the fourth quadrant, cosine is positive, so 1 minus positive 1/2 makes it 1/2. And if we put 2 pi, cosine of 2 pi, just the same as 0 is 1. 1 minus 1 makes it 0. So we have those pairs. So you can use this, or you can use the fact that what I just mentioned and see the other one, the other half, okay? And of course, if you have a polar grid, it makes it easier to graph it. All right, we want to graph r equals 3 plus 2 cosine theta by plotting points, and again reminding you of the symmetry. Let's quickly look at another example of a symmetry. So we are going to r equals 3 plus 2 cosine theta. We are going to replace the theta with minus theta. Normally when cosine is involved, that works. As you know, cosine of minus theta is the same as cosine of theta because it's an even function. So this is the same as cosine of theta. So that works out. And the test works. It's symmetric with respect to the polar axis, or we can think of it again as the x-axis. If I change that to pi minus theta, and I remind you that cosine of alpha minus beta is cosine alpha cosine beta minus sine alpha sine beta. Therefore, this part becomes cosine pi cosine theta plus sine pi sine theta, and cosine of pi is -1, sine of pi is 0. So we get 3 minus 2 cosine theta, which is not the same. Again, you are looking for this test and you want to see whether you get an identical equation. We got an identical equation in the first case. In this case, is this identical to this? No. Then the test fails, which means it's not symmetric with respect to the line theta equals pi over 2, or you can think of it as y-axis. Let's replace the r with negative r. And it doesn't work. Let's replace the theta, because if you multiply this by negative, this becomes r, both of them become negative. So the answer is no. If we replace it with theta plus pi, I'm going to leave it for you to see that this one won't work either, because all you have to do expand this. Okay, just the way we expanded this one, you guys expand this and you see that no, it's not. And so we are going to plot pairs, and of course bear in mind that we know it's symmetric with respect to the x-axis or the polar axis. Okay, again, let's pick up a few easy points. In fact, because we know it's symmetric with respect to polar axis, if we do half of it and then we from 0 to pi, the other half repeats, in essence, it's symmetric. So for example, if I put 0, I get 5, because cosine of 0 is what? 1. 2 plus 3, 5. If I put pi over 6, then I'm going to replace the cosine with square root of 3 over 2. With the 2 cancel each other. So pi over 6 gives me 3. plus square root of 3. Pi over 3 gives me 1/2. 2 times 1/2. 1 and 3 is 4. Pi over 2 gives me 0 here, so just 3. 2 pi over 3, the same as pi over 3, but negative. So 2 times negative 1/2, which makes it negative 1 and 3 positive 2. 5 pi over 6 is the same as pi over 6, but negative. So 3 plus 2 times negative square root of 3 over 2, or 3 minus square root of 3. And of course, pi gives you negative 1, 2 times negative 1, with 3 is positive 1. So again, I'm showing you this can be done, class, easily. Okay, I hope everybody's fine with that. It's really not too bad, but just in case. Okay. So we write the following pairs. We write the following pairs, and we are going to plug them in. For example, 0, 5. 0 is this, and 5 would be 1, 2, 3, 4, 5. So there. I want to go with the easy one, 4 and pi over 3. Pi over 3 or 60 degrees. We have 4. So roughly 1, 2, 3, 4. Okay. 3 pi over 2, pi over 2 or 90 degrees. Pi over 2 or 90 degrees. 3 means 1, 2, 3. Okay. Two pi over 3 or 120 degrees, and 2. So 1 and 2. Again, I want to do the easy one. 1 and pi. Pi is on this side, okay? 180 degrees. 1 is here. Okay. And so if I were to graph this, just for the sake of argument, and this is not going to look that good, but I'll show you a better graph, of course. So if I were to put them together, then use the fact that it's symmetric with the polar axis. Something like that, okay? I'm going to erase that and show you a much better graph, of course. Okay. This is called a limicon without an inner loop. Now, this is a limicon with an inner loop. So 2 plus 3 cosine theta. 2 plus 3 cosine theta. If you recall the other one, this number was larger than this number. Again, we are going to go with easy choices. Okay. And I'm going to do a few of them. 0 plus gives us 1 here. So 2 plus 3 is 5. Again, I'm choosing common arcs. Power 6, again, it gives me square root of 3 over 2. So 2 plus 3 times square root of 2 over 2. Power 4 gives me square root of 2 over 2. So 2 plus 3 times square root of 2 over 2. Power 3, the easy ones. pi over 3 gives me 1/2 times 3 is 3/2 with 2. 2 plus 3/2 is 7/2. Pi over 2, 0 gives me 2. 2 pi over 3, the same as pi over 3, but negative. So negative 1/2 minus 3/2 with 2 gives me 1/2. Pi gives me negative 1. 3 times negative 1. Negative 3 plus 2 is negative 1. 4 pi over 3 is the same as pi over 3, but negative. So it gives me 3 times negative 1/2. They add up to 1/2. 3 pi over 2 gives me 0 here, just 2. 5 pi over 3 gives me the same as pi over 3, positive 1/2. So 3/2 with 2, 7/2. 2 pi is the same as 0, which is 0, 5. And you can see the pairs. Again, class, these are the pairs we are going to use. And the moment we see cosine, if we replace the theta with minus theta, it works. So clearly it is symmetric with respect to the x-axis or the polar axis. I say x-axis, I want to remind you that polar axis in essence is the same as that. So if we want to go with the easy points, for example, 5, 0. So this is the 0 degree, 1, 2, 3, 4, 5. Okay. 7/2 pi over 3. Pi over 3 is 60 degrees. Okay, along this line. Okay, 1, 2, 7/2, 3.5 is somewhere here. Okay. Pi over 2 means 90 degrees. And 2, 1 and 2. Negative 1 pi. Here's pi, everybody. Here's pi, right? Or 180 degrees. 1 would be here, but negative 1 takes us this way. And right here, this one is the loop that they're talking about. And because it's symmetric with the polar axis, this is good enough if I were to go with that. Okay. However, this one, 2 and 3 pi over 2 means this is 90 degrees. This is 270 degrees, or 3 pi over 2. We want number 2. So 1 and 2 here, and that's another one. And you continue with this one. Okay. So let me erase it's gonna go through the pole, and all you have to do, set this equal to 0 and solve. It gives you the specific angle that will take you there. Okay, let me erase this. Everybody, let me erase this to give you a better graph. So this one, we don't have the common arc. I want to make sure everybody understand that there is an angle that takes us to 0. And how do you solve that? Set this equal to 0. And when you solve that, it doesn't give you a common arc, okay? But it does take you to 0, okay? All right, we are going to graph this function, and this is a rose as far as the terminology is concerned. So let's discuss the symmetry. First, we are going to replace the theta with negative, and it works out because everybody knows cosine of theta is the same, or 2 theta, doesn't matter. So the test works, and it makes it symmetric with respect to the x-axis or polar axis. Second case, pi minus theta. and you are going to distribute the 2. We get 2 pi minus 2 theta, as you know, because it's even multiples of 2 pi. Because this is even multiples of theta, this is the same as cosine of negative 2 theta, which is the same as cosine of 2 theta. So that works. The graph is symmetric with respect to pi over 2. And you don't have to check the next one. You can check it, or just remember, if it is symmetric with respect to both cases, number 1 and number 2, which means if it's symmetric with respect to the polar axis, as well as, remember, polar axis like the x-axis, as well as theta equals pi over 2, in essence, the y-axis, then it is symmetric with respect to the pole. You don't have to check it. But I highly recommend, if anybody has any doubts, you check that. You see that one of them will work. By the way, as long as one of these two work, it means symmetric with respect to the pole. So here's what's going to happen. Again, we are going to go with easy points, and this is a rows, and normally you can use a calculator to graph it, but what happens is that rows has so many pedals, and basically because this is 2 theta and this is an even number, it gets multiplied by 2. In general, I'll show you in a moment a general case. So easy numbers, and we're going to go with the first arc 0 to pi over 2. First arc 0 to pi over 2 of the function. Remember that there are 4 arcs for sinusoidal functions. And so for 0, if I put 0 here, I get 1, 2 times that makes it 2. Pi over 6. 2 times pi over 6 is pi over 3. That means 1/2. Cosine of pi over 3 is 1/2. 2 times that makes it 1. Pi over 4 times 2 makes it pi over 2, which makes it 0. And cosine of 0 is 1, so that's 2. Pi over 3 times 2 makes it 2 pi over 3. Now 2 pi over 3. Pi over 3 cosine is positive 1/2. 2 pi over 3 is negative 1/2 times 2 makes it negative 1. Pi over 2 times 2, because of this class. Again, let me just do this. I want to make sure. Because of this, I'm multiplying this by 2. Okay, everybody? I'm multiplying all these angles by 2. Pi over 2 times 2 makes it pi. What is cosine of pi? Negative 1. Therefore, times 2, negative 2. Here's the pairs. So 2, 0. So assuming this is to scale, so we have 2, 0. This is the 0 degree, and 2 means 1 and 2 here. And then 1 and pi over 6. Pi over 6 is 30 degrees. So it's here. The first one. Okay. 0 and pi over 4. Remember what happens to 0. Regardless of this angle class, if in general, let me just write this. Pole can be represented with 0 theta, any angle. Okay, so that's the pole. And just for the sake of argument, it's moving in this direction. Negative 1 pi over 3. So pi over 3 is 60 degrees. 60 degrees. So this is the line. And because this is negative, we move that way. Okay, negative 1. Now minus 2 pi over 2. So here's pi over 2, 90 degrees class. If we had 2 would be here, but it's negative 2, so we go the opposite side, 1 and 2. So right here, this is the graph, everybody. This is the graph. Only a portion of it. I'm showing you a portion of it. Let me, okay, just a portion of it. If you go with the other 3 arcs, you end up with this graph. And to make sure everybody understands what we're talking about, I'm going to show you with calculator. You make sure it's in polar mode, and you put 2 cosine 2 theta, and when you see it, it starts moving, okay, in the following manner. Okay, let me see if I can. So it moves this way. This way. This way. This way. This way. This way. Go back. And that's a rose. Now, I want to give you the general idea. Rose curves are characterized by equations of the form r equals a cosine n theta, r equals a sine n theta, where a is not 0, and have graphs that are rose graph if n is not equal to 0 is even. The rose has 2 times n petals, and if n is not equal to plus minus 1 is odd, has to be larger than. The rose has n petals. So if it's odd, n petals. If it's even, 2 times that. Lemniscates are characterized by the equation of the form r squared is equal to a squared sine 2 theta, r squared equals a squared cosine 2 theta, where a can't be 0, and have graphs that are propeller shaped. I just wanted you to be exposed to that.